My name is Michael, and I'm going to be teaching the AirSWOT portion of the workshop. So I assume most of you will be following along on Google Colab. If you do run these notebooks on your own local machine, there's a little difference between how to run it on your local machine versus how to run it on Google Colab, but that it's mainly an issue for the third module. So we'll get to that later, but just something to be aware of. I assume most of you, though, are probably running it on Google Colab. So this part of the workshop is split into 3 modules. The first module is an introduction to AirSWOT and to the AirSWOT data products. So we'll go through the data products and what each file is and take a quick look at the data. And then the second module is how to take those data products and get estimates of water surface elevation and water surface slope, which is really the whole point of AirSWOT, is to get 3D water surfaces. So the elevation of the water surface and the slope of the water surface so that we know which direction the water is flowing. And then in the last module, we're going to compare AirSWOT to some in situ data from water level stations and talk a bit about how to convert between vertical datums, which is very important whenever you're trying to compare remote sensing to field measurements. So hopefully you have the link to this GitHub for this portion of the workshop. And I just clicked on the under module 1, this first open in collab button. And hopefully you see something like this on your screen. So there's an overview of AirSWOT here. I'm not going to read all of this, but if you're interested, you can take a look. I'll give a brief overview. So essentially, AirSWOT is an airborne radar system that was originally built as a test radar for the SWOT mission, which Mark mentioned this morning is a spaceborne SAR mission that's planned to launch at the end of this year. And AirSWOT is different from SWOT in a number of ways. One way is that, as Mark mentioned, we're not limited to the satellite revisit period of SWOT. With AirSWOT, you can collect data 30 minutes apart, just repeat passes of the aircraft, and however many flights you want to collect, you can look at the water surface over multiple consecutive days. And by doing that, you can see the tide rising and falling in a way that, unfortunately, you can't really do with spaceborne data. So there are essentially 3 different processing levels of AirSWOT data. And the first one, the lowest level, is the level 1B interferogram products. Those are mainly of interest for those of you who are interested in radar remote sensing and processing of radar data, which probably most of you aren't. Probably most of you just want to use the data to learn interesting things about the hydrology of the area. So I'm not really going to talk about the level 1B products today. If you are interested in those, please feel free to ask me questions later. We're mostly going to look at the level 2 and the level 3 products. So the level 2 products are essentially just GeoTIFF, geocoded maps of the AirSWOT imagery. And then the level 3 product is a comma-separated values file where we've taken the level 2 product and we've done some filtering and averaging and down to get kind of just points in river channels or points in lakes that just tell you the water surface elevation in that water body or in that position along that river channel at a certain time. So I'm going to start by talking about the level 2 data products, which is what we'll spend most of the time talking about today. So the level 2 data products, there's a pre-Delta-X dataset, which is from 2015. And then we also have the Delta-X spring campaign data, which is available as a preprint. I'm going to open that link just to show you. So this is the level 2 data for the spring campaign. The fall campaign data should be available soon. And the level 3 data from Delta-X should also be available soon, but it's not available yet. So for this tutorial, I'm going to show level 3 data that was collected in 2015, but it's very similar. So the level 2 data, there are these .ann files, which are just text metadata. And what we're mainly interested in, if I skip ahead here, is these geotiff files. And essentially, each level 2 product is identified by the date and time that that flight line was collected. So for example, this file was collected in 2021 on April 18th, and it was collected approximately at 19 hours, 47 minutes, 53 seconds. And these are all in UTC time, which becomes important later when we're comparing it with the in situ data, which is generally in local time. And you'll notice that after each flight line ID, there's a number of files. So there's .err.tiff, .hgt.tiff, .inc.tiff, .mag.tiff, and so on. And each of these is a different data product. So the ERR is the height error, and the HGT is the actual height, and the INC is the radar incidence angle. And I'm going to show you each of these files and talk about what each of them is for. But just to give you an idea that that's basically how the level 2 data is structured. So here you can see in this image, this is just a screenshot from QGIS where I've loaded in some of the AirSWOT height files, so those hgt.tiff files for the April 1st flight. And I just loaded them in to show an example of what those look like. And if you want to do something similar, you can do the same thing. If you have downloaded that data, if you have the level 2 data on your system. So if you just have I'll show you the height geotiff file first, because it's the main product that we're interested in with AirSWOT.
So Michael, this would be in the L2 folder? Is that correct?
Yes, it would be. So yeah, I should show you where it is on Google Drive, probably. So it's going to ask me to verify myself. It does this every time. So in the Delta-X workshop folder, all of the data that we're going to use today is if you go to the tutorials and then _AirSWOT, there's a few different folders here. There's level 2, L2, which is all the level 2 files that I'm going to talk about today are in that folder. And then L3 this contains the level 3 product that we're going to look at today. And then the station data folder contains some of the in situ data we're going to use in the third part of the tutorial. And the water mask is a water mask file that we're going to use in the second and third parts of the tutorial. So, if you look through the level 2 files, I'm going to skip ahead here. I'm going to start running the actual Google Colab notebook. And it's going to ask me to confirm.
Hey, Michael, can you maybe zoom in a little bit?
Oh, yeah.
I know we're following along on our computers, but it's a little small.
Sounds good. Let me try zooming in here. So as in the previous notebooks, you just want to make sure that it connects to your Google Drive. which it should be doing. Let me zoom in a little more, maybe. How is that?
That's good. Yeah.
Okay, great. So that cell finished running, so hopefully it finished running for you as well. In the next cell, this just specifies the data path. So if you're running it on Google Colab, this path here should work. If you have a shortcut to the Delta-X Workshop folder in your drive, like for the previous modules, this should work. You shouldn't have to change it. If you are running it on your own machine, you just want to change this to point to wherever you've saved the data. And now I'm going to give an example of loading one of the products using GDAL and then displaying it. So this is just the file that we're loading, so it just points to the file relative to that data path that we specified above. And then we use GDAL to open the file, and we load the product data as an array using GDAL. And in the AirSWOT data, the void data has a value of minus 10,000. So we just set anything with a height of minus 10,000 to not a number, just to mask them out. And for those of you who are unfamiliar with GDAL, what I've done here is I've just loaded in the geotransform using GDAL, which just specifies the origin and the spacing of the grid that the data is on in map coordinates. And I just use that to calculate what the extents of the data are for this plot. And then this plots the data. So you should have something like this image. And so it shows the UTM X coordinate and the UTM Y coordinate. And then this is the .hgt.tiff file. So it's the AirSWOT height above the WGS84 ellipsoid. So all of the HGT files from AirSWOT are with respect to the WGS84 ellipsoid. And later on, we'll talk about how to convert that so that you compare it to other data sets that are not with respect to the WGS84 ellipsoid. Generally, a lot of water level data sets here will be with respect to NAVD88, the North American vertical datum, which is a geoid model. So we'll talk about how to deal with that later on. So when you look at the height file here, I want to make an important note, which is that while we use AirSWOT to get water surface elevation in open water areas, in the level 2 products, as you see here, it also includes land and wetland areas because we haven't masked the data yet. That's something that we have to do to get water surface elevation from this data. So let me show you the height scaling that I'm using. So I think this was just the default that it used when I loaded the data. So the minimum value is about minus 27 and the max value is minus 14. So yellow is the highest heights that are in this image. And we see some of these really high areas. And if I toggle the AirSWOT data off and look at the Google satellite imagery underneath, you can see that some of those tall areas where we see yellow are also line up with places where there's forest. So it's important to note that AirSWOT, the height that it measures is really just the height that of the objects that reflected the radar signal. So in open water areas, it's the height of the water. And if there's forest, it's height of trees in the forest, or in the wetlands, it'll be the height of the grasses. So it's always very important to mask out these areas if you want to get an accurate estimate of the water surface elevation. And whoops, you can kind of see that at the edges of the channel too. There's kind of a thin line of higher elevation values on either side of the river, which you can hopefully see here. And those are trees at the side of the river as well. And if I zoom out a little bit, so this is the Wax Lake outlet here. And this is Wax Lake at the top of this flight line. And as we go down, this also includes the Wax Lake delta. So I'm going to switch back to Google Colab. And so now that we've looked at the HGT or the height file, I'm going to look at the next type of data, which is the .mag.tiff. So I'm going to run this next cell here. And wait for that for a moment. Hopefully everyone's following along still. Is anyone not following along, or? Okay, I'll take that as it's okay. All right. So sorry about that. Okay, so this is the mag file, which is the backscatter magnitude. So this is more like just a radar image. So it just tells you how reflective to the radar waves that AirSWOT uses each pixel was. And you can see here that AirSWOT backscatter tends to be brighter, first of all, over the water than over land. And it's a lot brighter at this side of the image than it is at the other side of the image. And the reason for that is that one thing that's a little different about radar remote sensing as opposed to many other types of remote sensing is that AirSWOT looks to the side. So for this particular flight line, the aircraft would have been flying, hopefully you can see my cursor here, but AirSWOT would have been flying starting from down here at the bottom, would have been flying parallel to this track up towards the top, and it's looking to the left. So in the parts of this image that are closest to the aircraft, it's looking at a steeper viewing angle, which means that you tend to get more reflected radar waves from the ground. And then as you look more to the side at a more oblique angle, you get more of the radar waves scattering away from the radar, so it tends to be darker. And this, the part of this that is probably the most important to us is the fact that this means that the performance of AirSWOT and the amount of noise in the height estimates also varies with incidence angle. And generally, the heights will be less noisy close to the radar, and they'll be noisier farther away from the radar, which we'll see a little bit later, some examples of that. Yes. Yes. So, well, the correction factor is the data is scaled so that it's scaled to what we call sigma naught. So it has been corrected for the area that the radar is scattering from on the ground. But even with that correction, there is still incidence angle dependence. One way to think about it, I guess, is that, especially with water, since water is a fairly smooth surface, the incidence angle is really important. So what I was talking about when we're at a very steep incidence angle, you get a lot of reflection. And at a far angle, you get less reflection. And you see this in the image. It's not really something to correct because it's more of just the natural phenomenon of how the radar scatters back to the sensor. And similarly, the way that the backscatter depends on the incidence angle is different for water than it is for, say, vegetation. So if you looked just at the vegetation in the image, you actually wouldn't see as much incidence angle dependence. But from water, you see a much more incidence angle dependence since the water scattering is much more dependent on the angle since it is such a smooth surface relatively. So hopefully that makes sense. So that was the .mag file, which is the AirSWOT backscatter. And we also have a mag_ns file, which is noise subtracted magnitude. So it's very similar to the backscattered magnitude, So this is, I would say, one correction that we do release the data from. And you can see this here, this plot of the backscatter after noise subtraction. And the thing is that when the signal is high, you don't really see much difference before and after subtracting the noise. But when the signal level is very low, you see a much bigger difference. And I created a plot of that here in the next cell, which I'm now running. So this is the difference between so this is the magnitude of that noise correction. And you see at the left side of the image here, which you'll recall is where we're farthest from the radar, so we're at the shallowest viewing angle, the noise correction is much greater. So it's just something to keep in mind that the noise level varies quite a bit across the swath of the image. So now I'm going to show the ERR file, which is the height error file. So when processing the AirSWOT data, we have an estimate of what the expected standard deviation of the height error is for each pixel. And that's what's in the ERR file. So the ERR file is in units of meters. And you can see, as expected, the height error is greater on the left side of that image, farther away from the radar. And it's less close to the radar. But even close to the radar, you can see the height error can be up to 1 meter. At far range, it can be multiple meters. And that's way too large for the types of applications we want to use it for, where even a water surface elevation change of centimeters can be significant. So what we do is we always want to average AirSWOT data down. So we want to aggregate a lot of pixels together from the AirSWOT data rather than just using one pixel, because at the individual pixel level, the data is just too noisy. So we're going to talk about that in the next module in terms of masking out the parts of the data we don't want, and then smoothing and filtering what's left in order to get an estimate of the water surface elevation. And the next level 2 product is called the CORR file, which stands for correlation. And this is very similar to the error file, but it's kind of the flip of that. It scales from 0 to 1, and the higher the correlation, essentially the less noise in your estimate. Essentially, how AirSWOT works is it takes 2 radar images from antenna that are at slightly different positions, and this is the correlation between the 2 radar images, the complex correlation, I should say. And so the higher the correlation, the better. And that's what you see here, where generally we get the best correlation values kind of near the middle of the swath, and then it's a little bit lower right at near range, and then it's lower at far range. So we get the best results kind of in the middle of the AirSWOT image. And the next level 2 product is the INC file, which is the incidence angle of AirSWOT. And this is the viewing angle that I've been talking about. So the data is in units of radians in the GeoTIFF. So here I've just converted it to degrees using NumPy. And as before, all of these examples, I always just set all of the minus 10,000 values to not a number, just to make sure that those don't stay in the image. If you don't do that, then you'll have a bunch of minus 10,000 values that are still there. So this is the incidence angle. So you can see close to the radar here, it gets down to a value of a few degrees. So essentially that's just the angle between aircraft nadir. So from the aircraft looking straight down, and then the angle between that straight down versus wherever you're looking off to the side. And then the AirSWOT incidence angle goes up to about 27-ish degrees. But as I mentioned, we tend to get better performance in the middle of this range. So usually we don't actually want to use all the data all the way out to the edge because it starts to get just noisier and noisier. And there's one last file, which I will mention since it is up on the site, and I want to make sure that I talk about all the files. I'm guessing this file won't be of interest to most of you, though. This is essentially a bit redundant if you have the height error file. This is really, this file is called DHD-Phi, and this file is essentially the height sensitivity of AirSWOT. So the DH is height, and then the D-Phi is the interferometric phase of AirSWOT. So it's the phase measurement between those two radar images that were collected from different positions. So what this tells you is essentially how sensitive AirSWOT is to vertical height at different parts of the radar image. And as you can see here, kind of close to the radar, this value is around -2, -1 to -2. So that means for each radian of phase, you have about a meter of height. So AirSWOT's less sensitive at that part of the swath. And then at the far swath, far end of the swath here on the left side of the image, these values go down to like -12, -13. So it's a lot more sensitive. So that's why at the far edge of the image, we have bigger height errors, is because the sensitivity of AirSWOT to height is greater at that far edge of the image. So that's all of the level 2 data product files, and we'll revisit those in the second module of the tutorial. But for now, I'm going to change gears a little bit. I'm going to talk about the level 3 data products, which I think are probably more useful to most science users since they're a higher processing level. Before I move on, does anyone have any questions about any of the level 2 data products or? Oh, yes, please.
Flight path. It appears that the flight path is to the right side of east side of that image.
Yes.
Is that correct?
Yes.
And now are we talking about one broadcast radar signal and 2 antennas receiving?
Yes, that's a great question. Yeah. So yes. So the aircraft was flying along the right side of that image, looking towards the left, and yes. So one of the antennas for AirSWOT it always transmits, and then we receive from that antenna that transmitted, as well as another antenna that's separated by some distance. And there actually is another antenna as well that's, instead of being across the flight track from the first one, is along the track. And we use that antenna to compensate for the motion of the water, which I hadn't really mentioned since we processed that out. So in the final products, you don't really need to worry about it. But technically, the motion of the water also contributes to the radar measurements, and we need to remove that effect.
So the radar swath is only collected on one side of the aircraft?
Yes, that's correct.
Okay.
Yeah, which is different from SWOT, actually. Right. So if that was why you're asking, the SWOT satellite collects on both sides of the satellite as it travels, but AirSWOT only collects on the left side.
Thank you.
Yeah, you're welcome. So looking at the level 3 data products, these are a little bit easier to use than the level 2 products. And so this is the highest processing level of data that we release for AirSWOT. And sadly, they're not available yet for Delta-X. So we're going to use some level 3 data from the pre-Delta-X campaign, which was collected in 2015. But the level 3 data from the Delta-X campaign should be available pretty soon. I think we're delivering that at the end of June. So the level 3 data is just a CSV file, which can be displayed in QGIS. So I'm going to do that now. And there's some instructions here in the Collab notebook, but you can also follow along with me if you have QGIS open and if you have the level 3 data set. So to view this in QGIS, what you want to do is go up here to the top where it says layer, and then you want to go add layer, and then add delimited text layer. And then under the file name, you want to go to wherever the data is saved. So I'm just going to point it to the level 3. And oh yeah, thank you, Talib. Talib put the link in the chat as well. So I'm just going to go to the CSV file that I downloaded.
Also, Michael,
Oh, yeah.
there's a question in the chat.
Oh, great.
Is there a pre-processing for L2 products to get rid of the near range, far range phase ramp?
Yeah, essentially we do calibrate that out. So we have some calibration steps that the idea is we cross-calibrate the radar because the way we flew the aircraft, we made sure that each flight line overlaps with another flight line at about 90 degrees or so difference in heading. So all of the lines crisscross each other, and then we use the places where the lines are overlapping to try to calibrate the phase. So that's already been done by this point in the processing. So I'm just going to point QGIS to that level 3 file, and I'm just going to say open. And there are some options here, and you can kind of see the data down here. So we want to specify that the geometry of the CSV file is in point coordinates, like the default. And QGIS is pretty smart. It thinks the longitude field should be X and the latitude field should be Y, which is correct. And then the geometry coordinate reference system, which is what this stands for, we're just going to leave that at the default, which is EPSG 4326, which is just the WGS 84 ellipsoid in longitude, latitude units. In this file, we also include the UTM coordinates for each point as well. So if you wanted to, you could change this X field from longitude to coord X, and you could change the Y to coord Y. And in that case, instead of WGS 84 here, you would change it to this one, which is WGS 84 UTM zone 15 north. And that's the coordinate system that all of the level 2 files are in. But for the level 3 file, we give you both. We give you the UTM coordinates if you want to use those, and we also give you the latitude and the longitude. So I'm going to switch back to longitude and latitude just for this example, but it contains both. So after you set those options, you just say add, and then I'm going to turn off the other layer I was looking at, and now so zoom out a little bit, and you see now we have all of these points along the Wax Lake outlet. So for the Delta-X level 3 products, we'll have more data, and we'll have other river channels and lakes and so on. The Delta-X data covers a lot wider of a study area, but for the pre-Delta-X data, we only generated profiles in the Wax Lake outlet. So that's all you see here. And so each of these points, which I'm going to zoom in now, and if you look at each of these points, you can inspect them like Daniel showed using this Identify Features button. And if you click the points, you can see that each point in the CSV file has fields for so this first one is as a channel identifier. So for the Wax Lake outlet, we just used WLO. So that's how you know that these points are from that channel. And then it has the date and the time, which again are in UTC, not local time. And then there's another field here called a long channel distance. And so what we do when generating the level 3 products is we convert all of the map coordinates into a channel coordinate system using the center line of the river. So we have a river center line that goes along the Wax Lake outlet, and then we project the AirSWOT points onto that center line, and so we can have a value that just gives you the distance along the channel that you've traveled, starting from Wax Lake being at 0. And then in addition to that, we have, as I mentioned, the X and Y UTM coordinates, the longitude and latitude. And then what you probably care the most about is the water surface elevation. And we report this with respect to the NAVD 88 geoid, as well as with respect to the WGS 84 ellipsoid. So this is the same datum that the level 2 products are referenced to, but we also provide this one in the level 3 products, since it can be a little simpler to use. And we also provide an estimate of the uncertainty in the elevation. And so this is, again, an estimate of the standard deviation that we expect the height errors to have. So in this case, for this point, it's 7.4 centimeters. And as you'll recall in the level 2 products in the height error file, the height errors were a meter or more. But this is a lot smaller because we've averaged a lot of AirSWOT pixels down to produce these points along the channel. And one thing you can do in QGIS, if you want, when displaying these, maybe that'll stay on better. By default, they all display as one color, but if you change this from at the top here where it says single symbol, you can change it to graduated.
Excuse me, do you mind if I ask
Yes.
a question?
For sure.
Earlier you had talked about how many flyovers you did for Delta-X. Can you just remind me how many transects there'll be? Is it like once in fall and spring?
There'll be quite a few. So I think in spring we had 10 flights. And I think of those 10 flights, 4 were in the Atchafalaya Basin, and then 3 were in the western part of the Terrebonne, and then 3 flights were in the eastern part of the Terrebonne. And during each flight, we cover the same flight plan multiple times. Essentially, they just collect all the lines, and then they start over and collect them all again. So on each flight day, each channel was probably collected 4 times. Sometimes it's less than that because in some cases, if the wind speed was very low, sometimes you get a situation where you don't get enough radar signal from the water. So we have void data sometimes. But in ideal conditions, you'd expect to get about 4 flyovers per flight and then probably 3 or 4 flights. So probably like 12 to 15 repeats of this channel.
Okay. So like when you would do the 4 times back and forth, how long would that usually take? Because I'm trying to think of how to connect that to like a USGS gauge or something, right? Kind of matching those up.
Yeah. So usually I think each AirSWOT flight took about 4 or 5 hours.
Mm-hmm.
So each repeat was probably like an hour or so apart-ish. It depends on the different flight plans had a little different like lengths of the lines and so on. But yeah, you're looking at probably AirSWOT collected the same point every like hour or so, probably 4-ish times on each day.
Okay.
They did time the flights so that we tried to capture interesting parts of the tidal cycle. So there would be a flight that's rising tide and another flight that's decreasing tide and so on.
Mm-hmm.
So when you're comparing it to the like USGS or like the CRIMS data, of course, those stations, they collect water levels every like 5 minutes or something. So they're a much denser time series than AirSWOT is. So the advantage of AirSWOT is more in the spatial dimension, that you can see like a continuous water surface, but the temporal sampling is a lot less than the water level gauges.
Okay, great. Thank you.
Oh, yeah, you're welcome. Yeah, if you'd like to display the CSV file, you can also color it by the height of the water. So if you choose graduated up here, and then next to value, you choose which field you want to color the points by. So in this case, I'll choose water surface elevation NAVD 88, and then I'll classify them. So you click the classify button, and it'll assign colors based on the water level. And if I hit OK, now instead of all being the same color, our points should now change in color based on their water level. And you can see that upstream in the channel now, these yellow points have higher water surface elevation, and then they get lower and lower, and then they get lower still as they reach the delta and then the ocean. Yes. Oh, yes, thank you. That's a good question. I'm sure other people were wondering that as well. It goes straight through an island because that's where the center line was. It does not include data from the island because the island was masked out, but it includes data on either side of the island, and then the points got put in the middle. So that may be a little confusing, but hopefully that's clear that in cases like this, it's the point is really just the centroid point of the data that was used to estimate that water level. That's something I want to improve for the Delta-X products, because this center line was just a manually drawn center line, and I think we could probably do better with a little more natural center line. So now that we've displayed the level 3 data in QGIS, I want to show some examples of how we can plot and look at the data in Python. So I'm going to skip over this because we covered this in QGIS, but the instructions are all here in the Google Colab. So now we're going to load this CSV data into Python, and we're going to use pandas to do that. And if you're not familiar with the pandas Python library, you can really just think of it as being really similar to an Excel spreadsheet in terms of how the data is organized. And since this is a CSV file, you can also load it in Excel if you want to. And if you want to plot it in Excel, you can certainly do so there too. So I loaded the AirSWOT data using pandas, and then I just printed the AirSWOT data. So this is what the data frame looks like that we loaded in from the AirSWOT. So each of these fields that I talked about in the point data, and then the water surface elevation for each point, and then the uncertainty. And you can see the uncertainty varies a little bit as we go along the profile. Not a lot, just a little bit, because some of the samples were averaged from more pixels than others. So I think I talked about all the columns that are in the file, so I'll skip over that. And then here, this code is going to plot the water surface elevation from the file versus the along channel distance that I talked about. And this will show us how the water surface elevation varies along the Wax Lake outlet. So this plot now shows us the water surface elevation with respect to the NAVD 88 geoid. And then this is versus the along channel distance. Starting at the Wax Lake itself is 0, and then it just continues down the channel until we reach the delta. So this is a plot of that profile that matches these points here. And so this tells us how the water surface elevation varies along the channel, which is useful. But another thing that we want to do with AirSWOT is look at not just the water surface elevation, but also the water surface slope. So we're going to look at how to calculate that now from the level 3 data. So here we just calculated the water surface slope by taking using the NumPy gradient function. So just taking the change in water surface elevation divided by the change in the along channel distance. And here we multiply the water surface elevation by 100. So it's in units of centimeters. And the along channel distance, I've already converted to units of kilometers, as in the above plot here. So when we calculate this water surface slope, it's in units of centimeters per kilometer. So it's centimeters of water level change per kilometer of along channel distance. We use those units because they're a little nicer to deal with than having a slope that's 0.00 something, because the slope is extremely small in most of these places. So when you run this cell, you should get a plot that looks like this. So this is an estimate of the water surface slope in the channel. And I've printed here the mean slope in the channel, which is about minus 3.8 centimeters per kilometer. And you see here that the slope estimate is kind of noisy. Not really sure we like that. The reason this is noisy is because the level 3 data is sampled about every 50 meters along the channel. So it's been kind of reduced in resolution compared to the original data. But we can smooth it and estimate the slope from the smoothed values in one step. So the code to do this is in this cell. So I use what's called a Savitsky-Golay filter, which is just from SciPy. And essentially that filter, it just fits a polynomial. It's just like a moving average, but instead of taking the average, it's a moving window that's used to fit a polynomial to the profile data. And because it fits a polynomial to the profile data, you can also take the derivative of the polynomial at each point. And that just gives you a smoothed estimate of the slope compared to what I did above, where I just estimated the slope directly from each point. The nice thing about this filter is you can choose how much filtering you want to do. So I'm going to show here results for 2 different window sizes. So this first one uses a window length of 2 kilometers. And here I just calculate that because it's 2,000 meters, and then each point along the channel is sampled 50 meters apart. And then similarly, we're also going to use a window length of 10 kilometers. And I use a window length of 10 kilometers because that's also the reach length that's going to be used by SWOT for estimating water surface slope. Most of the SWOT slope measurements will be on the scale of a 10-kilometer reach. So I want to show that as well. So I'm going to run this cell now. And these are the lines that do the filtering. So just using the 2 different window lengths, and this deriv equals 1 means we want it to return the derivative of the function rather than the actual water surface elevation. We want the slope. And the delta here is just the sampling along track. So it's 50 meters, but I've converted it into kilometers again so that our slope will be in centimeters per kilometer. And then this just plots the results. And you can see the results of that here. So our original slope measurements are in blue, and they were kind of noisy, didn't really like those. And then the orange line is the 2-kilometer smoothing window, which is a lot better. You can see that the slope reaches its steepest point around kind of 5 kilometers into the channel. And we may wonder, well, where is that? You know, where is it 5 kilometers into the channel? And if we're curious about that, we can go back into QGIS and we can use the ruler up here, the measure line, and we'll just click it, and we'll click our point in the wax lake as our 0, and then we'll just measure 5 kilometers. And it's about here. So this is about the point where the slope of the water surface is at its kind of steepest point, and then after that, the water surface slope smooths out, becomes less steep as we move past the intracoastal waterway and towards the ocean. And this green line in the plot is the 10-kilometer window. So this was kind of the same amount of filtering or averaging that would be used to estimate water surface slope from the SWOT satellite once it's launched. And you can see it captures most of the variation, but it doesn't quite get that peak in the slope values. So you can see this is one example where since AirSWOT is an airborne instrument, it does have a finer spatial resolution than is really possible from SWOT being a satellite. Yeah, that was why I used 10 kilometers, was just to compare with it, yeah. And also to show that in the case of AirSWOT, that's probably more filtering than you really need to do, unless you want to. Yeah, I think that's it for the first module. So just to sum up, so far what we've covered is how to load the AirSWOT level 2 and level 3 data using QGIS and Python. We've talked about the naming convention of the AirSWOT level 2 data files and what each of those products represents. And we've talked about the structure of the level 3 data and what each of the columns is. And we've also shown how to plot water surface elevation profiles from the level 3 data and how to calculate the slope from the level 3 data. Before I move on to the next module, is there any questions or anything unclear? Okay. So I'm going to close this first module now and go to the second one. So I'm just going back to the GitHub. Now I'm going to open module 2 in Google Colab. So now that we've gone over an overview of the data, this module is where we start looking more into, let's say you downloaded the level 2 data and you want to use the level 2 data to estimate water surface elevation in a water body that you're interested in. So how would you go about doing that? So as I talked about before, AirSWOT, since it includes land and wetland vegetation, the first step is always to use a water mask to filter out any non-open water pixels. And then after that, we do some outlier filtering to help get rid of any pixels with height outliers. And then we essentially just average the data to get estimates of water surface elevation over a large area. So for this module, I chose this lake. And this green point is a CRIM station that is near the lake so that we can compare with the CRIM station in the next module. But I'll show you where this is in QGIS. If I go back here, this is over in Terrebonne now because I want to show different areas for different parts of the tutorial. So I'm just going to go over here and there it is. So it's this lake right here. And I chose it basically randomly, mainly just because it happened to be close to a CRIM station, and it's fairly large, so it should give us enough pixels to get a good water surface elevation estimate. And so having selected our site of interest, now we need to figure out well, which AirSWOT flight lines actually cover that area. So I've gone through the data and I've selected these 4 flight lines. So there's 2 flight lines on April 16th and 2 flight lines on April 18th. And there is more data that covers this lake than that. But for the purposes of this example, I just wanted to use a few flight lines. And if you try to do this yourself, you might notice in the sample data, there's some flight lines from April 12th as well, which I was originally going to use for this example too. But then I realized there are some calibration issues with the April 12th data. So something to keep in mind, I think as Mark mentioned earlier, that the data is hot off the presses. So while doing this, I discovered some issues with the April 12th data over this particular area that we'll have to fix. So for now, I'm just going to use the April 16th and April 18th data. So same as before, we're just going to run the Google Colab setup. It's going to ask me some questions. So as before, just make sure it's pointed to the path where the data is. So if you're running on Google Colab, this should work for you. If not, just change it to point to wherever you have the files. So I'm just importing kind of standard libraries. So this OS module handles some of the file name and path handling. And then NumPy does a lot of help with arrays and calculations. And then I import GDAL for the geospatial stuff. And then I import matplotlib for plotting. And these are just the file names of those 4 flight lines that I found which overlap the lake that we're interested in. And I'm using the height files, of course, because I want to get the heights. I'm not going to use the other files for this exercise. As I mentioned, all of the level 2 products are in UTM coordinates, not in latitude, longitude. So we need to know the UTM coordinates of the lake in order to find out the position of the lake in the AirSWOT images. So you can do this pretty easily in QGIS. If you look at the bottom of the screen here, it'll always tell you the coordinates of your cursor position in whatever coordinate reference system you've chosen down here. So in my case, I'm using UTM zone 15 north, so it's the same as the data. So I just moved my cursor around, and then when it was approximately in the middle of the lake, I just wrote down the coordinates from QGIS, and those coordinates that I got are right there. So it's about 719,000 X and about 3,246,000 Y. So now that we have the coordinates of the lake, let's subset the AirSWOT data down to the area around the lake. So we're going to use GDAL to help with that. So I'm just running the next cell here. Just going to wait for this to finish. Great. So what I do here is I load the geotransform of the AirSWOT flight line. Here I'm going to, even though I have 4 flight lines that we're going to use to estimate the water surface elevation, I'm going to do the example just for the first one first by itself. And then after we've done it with the first one, I'll show you how to do it in the loop. And we'll do it for all the others using the same method. But I think it'll be a little easier to understand if we just start with one file. So we load that height product using GDAL, and we get the geotransform. And the geotransform is really just some numbers that give you the X and Y origin of the grid, and then as well as the X and Y pixel spacing. And this cell just prints those out. And I also have a function here that converts map coordinates to pixel coordinates. So it's pretty simple. Just you give it the X and Y coordinates, as well as that geotransform from the raster. And then the row is really just the Y coordinate minus the Y origin, and then you just divide by the pixel spacing. And that will give you the row and column of the image corresponding to the map coordinate. So this is the X and Y coordinates of the lake that I'm interested in. And then I convert those to a row and a column. So these are all the outputs from that cell. So this is the geotransform for the AirSWOT product, which tells us where that AirSWOT product is located. And it prints out the X and Y origin and the X and Y pixel spacing. And you can see the pixel spacing of the AirSWOT products is 3.6 meters. But in general, since we always do aggregation, we're usually aggregating pixels over like a square kilometer or so is the kind of scale that we aggregate to get a reasonable estimate of the water surface elevation. And then this is the image position of the lake in row and column coordinates. So now that we know where the lake should be in the image, we'll plot it to make sure that we are close to where we expect. So that's what I've done here. I calculated the row and column of the lake in the cell above, and I just convert them to integers so I can use them to index the array. And then I just cut out a image chip that's centered around the lake. Then I plot the image chip here. And you can see this is the AirSWOT height values around that image chip. And there it is. This red marker is the center of the image chip, which is the location I picked as the approximate center of the lake. It doesn't really matter. It doesn't really need to be exact as long as it's kind of close, because we're going to mask out the land areas and so on to figure out which pixels are actually in the lake and which are not. Since this is zoomed in, it's a little easier to see that this flight line was collected along a similar heading as the one I showed in the previous tutorial. So the aircraft was to the right of this image and it was looking to the left. So these parts of the image that are on the left are a lot noisier. Hopefully that's clear when you see it on the screen. And then as we move closer to the radar, you can see like the water in this river is much smoother, and the water on this side of the lake, the height values are a lot smoother than they are over here, where they become a lot noisier. So we found the lake in our data, and the next step is to filter out the non-water areas using a water mask. And I'm using a water mask derived from Sentinel-2 data from the following paper. But you could also use your own or use a water mask from all sorts of potential sources, or you could even just create your own by manually selecting the pixels in the lake if you want to. So to apply an external mask to the AirSWOT data, we're going to interpolate the value of the water mask for each AirSWOT pixel. So that's what we're going to do next. And I should point out that the functions in the cell below all assume that all of your files are in the same coordinate system. So for the purposes of this example, I converted the water mask to also be in UTM coordinates, just like AirSWOT, which is something that you can do with GDAL. So I'm going to run this cell now. And these are just functions to help with this. So I have a function to do a nearest neighbor interpolation at given coordinates. And then this function to interpolate a raster at the given X and Y coordinates. So it really just calls the function that we already looked at above to convert the map coordinates into image coordinates. And then it interpolates the image at those image coordinates. And similarly, this function just, since we've cut out a subset of our AirSWOT image, we don't want to get the X and Y coordinates of the full image. We just want the X and Y coordinates of that image chip, which is what it calculates here. It goes from rows and columns back to the map coordinates. So we're just going to use these functions to help us farther down. So now that all those functions have been defined, I'm going to run the next cell where we start doing the actual water masking. So the first thing we do is we load the water mask with GDAL, just like we did with the AirSWOT products. We load it in the same way, and we load it with GDAL, and then we load the data as an array, and then we also get the geotransform for the data. And similarly, the same rows and columns that we used to subset the image chip from the AirSWOT data, we're going to just take those same rows and columns and convert them into an image of rows and columns that's the same size as that image chip. So for each pixel in our image chip, we now know the row and column coordinates, and then we convert those from rows and columns back into map coordinates. So this is just using that function that I showed above. And then once we have the map coordinates, we can then interpolate the water mask at the same position as each AirSWOT pixel. So for each AirSWOT pixel, we take the closest water mask pixel using nearest neighbor interpolation. And then now the water mask, this interpolation function interpolates them as floating point values. So here I just convert it back into a binary mask. So wherever the water mask is greater than 0, that's water. And now I'll plot it here. So this is the water mask that we've interpolated to the same image chip as AirSWOT. Hopefully you can recognize here the lake that we're interested in. As you can see in the water mask, there's a number of channels kind of going in and out of the lake, as well as these rivers to either side. And for the purposes of this exercise, we want to estimate just what the water surface elevation is in the lake itself. We don't necessarily want to include all of these other areas. So how do we isolate the lake from the other areas? And one way to do this, if you want to kind of subset the data just to one water body, is you can erode the water mask, essentially. So using this binary erosion function in SciPy. So you can set the number of iterations, and I just increased it until it did what I wanted it to do, which is, if I run this cell, I will show you. So what I wanted to do is I just kept increasing the number of iterations of the erosion until it isolated the lake from everything else. So this is the water mask. I'll scroll up again just to show you. So this is what the water mask actually looks like. And then after we've eroded all of the water enough times, this is what it looks like now. So now all of the lake pixels are part of one contiguous area of water in the water mask. And now that we've done that, we just select all of the pixels that are part of this contiguous block. And that leaves us with this. So now we have a mask that just includes the pixels we want to average to get the water surface elevation and doesn't include any of the other pixels in the river channels going in and out of the river or anything like that. So yeah, and the code to do that is here. So it erodes the water mask, and then I use this label function, which is also from SciPy, to label each of the contiguous water bodies in the image, and then I just choose the water body labels that match the lake that we want in the middle. And that's how I got rid of the other parts of the water mask that aren't connected. And so now we have a mask that only includes the lake. So I'll run this next cell. And here we go. So I take a copy of our image chip, and I just call it image height lake chip masked. And now wherever the water mask is not true, we'll just set to not a number. So we'll set all the data to void, that it's not in that lake mask. And then we'll plot the AirSWOT data after the masking, which you can see is now here. So all of the other AirSWOT heights are void data, and we just have the AirSWOT heights over our lake. And there's another step I do, and I included it here because it's something I always do when processing the data, but it turned out not to really be necessary for this example because this is a pretty well-behaved area. In the next module, there's an example where it is important, but after doing the water masking, we also do a outlier filter. And so I have a function here that does the outlier filtering, and essentially it uses what's called a, oh, is there a question?
Are you concerned that the erosion function may have reduced the size of the lake?
I like that question because I'm not concerned. That's actually part of why I did it, because usually if you have water mask errors, which sometimes there's a little bit of misregistration, it's usually at the edges of water bodies. So usually if you have water mask errors, it's close to the land, or it's close to the place where the water changes into land. So I actually kind of like that it got rid of some of those areas at the edge of the lake, and that we're focusing on more on the center of the lake. Usually when I'm processing the data, I don't necessarily use the erosion function, but I will often set any pixels that are within 20 to 30 meters of land as, I usually filter those out too. I don't actually include them in the water body. Because yeah, from past experience, those are usually the places where you're most likely to have errors in the water mask. So here we have a function that does the outlier filtering, and it uses a median absolute deviation. So it's a two-tailed outlier filter. So essentially, it calculates the median of the data, and then it calculates the deviation from the median on either side of the distribution. And then it has a threshold, and it filters out everything beyond that threshold. And so we run the outlier filter, and then so we have I take here the mean AirSWOT height before masking, before the water masking, and then the mean height after the water masking, and then the mean height after masking and outlier filtering. So in this case, the outlier filtering doesn't really do much. As you can see here, there aren't really any outliers. It's a bit noisier on this side of the lake because that's again, we're getting farther from the radar, but there aren't any huge outliers here. So the outlier filtering kind of just eats up parts kind of just randomly throughout the lake. And it ends up that, for this example, let's see, where's the text? Oh, here we go. The outlier filtering really only changed the mean elevation by 1 centimeter. So it didn't really make a substantial difference. And but in the next example, in module 3, it does. But so the elevation of the lake that we've estimated is about minus 25.51 meters. And that's with respect to the WGS 84 ellipsoid. So now that we've done that for one of the flight lines, we're going to do that. Actually, wait, no, sorry, I got ahead of myself. The next thing we're going to do is actually to estimate the water surface slope of the lake. Because the advantage of AirSWOT is that even though we have to do some kind of aggregation or filtering to estimate the water surface elevation from this noisy data, we don't just have to take the mean, we can also fit a function to the surface, and we can use that to estimate the slope of the water in the lake. So that's what we're going to do next. And I have a function here to do that. And so this uses the NumPy linalg, which is linear algebra, and then that's the least squares. So it's just doing a least squares fit to fit a plane to the AirSWOT points. So you give it the x coordinate, the y coordinate, and the height. And then this function, as before, to give the slope in units of centimeters per kilometer. The X and Y values are converted to kilometers, and the Z value is converted to centimeters. And then I also take out the mean X and Y when I do the fit, so that the origin of the plane is basically in the middle of the data. And then it just uses a least squares function to solve for it. And when you do that, so these are the coefficients that we got from the fitted plane. And this last one is the height of the plane at the center of the lake, which you can see is very similar to when we just took the mean height, which makes sense because if you're fitting a plane to some data, generally the origin of the plane should be kind of at the mean Z value of the data. But what we really want from the plane fit is the X and Y slope, which are printed here in units of centimeters per kilometer. And on this plot, I've plotted an arrow, which is right here, where I take the X and Y slope and I plot that as an arrow. I multiply the slopes by -1 because I want the arrow to point downslope in the direction that we would expect the water to be flowing. And when you do that, you get an arrow pointed in this direction, kind of southwest approximately. So that tells us that according to AirSWOT, the kind of dominant slope of the water in the lake is in this direction. It's a little hard to tease that out in terms of, is the water flowing through this channel down here or through this channel, or is it just flowing through the wetlands? You can't really tell that. We don't really have enough resolution to really determine that. But we can tell that the overall average direction of the water in the lake is flowing in that direction. So having done that, the next cell essentially just repeats everything that we've already done for all of those raster files that we want to use that cover this lake. So, because we don't want just one water surface elevation estimate, we want to do that for each AirSWOT flight line because we want to see how it changes over time. So I'm going to run this cell now. And, uh-oh. Oh, whoops, I think I forgot to run one of the cells up here. And because I didn't run the cell up here, it's missing that function. So let me go back and then try this again. I think that should work this time. Oh. Okay, great. So this time it ran. So I'm just going to scroll down here. Without getting too much into this, it's really just the same stuff that I've shown before. It's just now we're doing it in a big for loop. So we just loop through each of those HGT files, and we load the data, and we set the void data to NaN. We calculate the image coordinates of the center of the lake. We cut out the image chip around the lake. We get the image coordinates. We get the map coordinates for that image chip. Then we interpolate the water mask, erode the water mask, label the part of the water mask that has the lake after erosion. Then we apply the mask, apply the outlier filter, and then the water surface elevation is just the mean of the heights that are left after the masking and the filtering. And again, I just do a plane fit to estimate the slope. This part is new in this loop. And what I'm doing is, as I mentioned, the AirSWOT product file names are the date and time that they were collected approximately. So I just take the file name and I just convert each part, like so year, month, day, hour, minute, second. I just convert all of it into integers instead of the string that was in the file name. and then I use a Python datetime object to keep track of that. So the nice thing about using datetime objects is it makes it much easier to compare with other data sets, if that may be at different times. It also makes it much easier to convert between time zones, which I'll show in the next module. So for each of those flight lines, we take the water surface elevation and the date time it was collected at, and the water surface slope in the X and Y directions. And then I just keep track of those in arrays. So each time we calculate a new one, we just append it to the array. And then at the end, it prints the results. So for each flight line, it just prints the elevation and the slope to the screen, and then it plots the time series. So this is the printed results. So for each date and time that we had a file for, this is the estimated water surface elevation, and these are the estimated slopes. And then this is the plot of water surface elevation versus the date time. So this is just the UTC date. So if you'll recall, the first flight we looked at was on the 16th of April, which are these 2 points. And then the second flight we looked at was on the 18th of April, which are these 2 points. And we see that during the April 16th flight, the water surface elevation was decreasing during the flight. And during the April 18th flight, the water surface elevation was increasing. And we'll compare that to the data from the CRIM station to confirm that that was actually what was happening. But we'll do that in the next module. So now that we are going to plot the same images I plotted before, showing the slope direction. This just plots that for each of the flight lines. So this is a plot of, this is just the slope vector for each of the flight lines. And then this is the image chip for each of the flight lines with the slope direction shown as the arrow on the image. So it's very hard to validate these slopes. It's a little easier in river channels. If you have multiple water level stations along the river, you can take the slope between the water level stations. In this case, since we just have one CRIM site nearby, it's really hard to validate these slopes, though we could compare them to the results of like hydrodynamic models and see if they agree with that. But haven't done that yet, so it's still we're still not really sure about these slopes. But in the next module, we will show how to validate the water surface elevations themselves using the in situ data. So, which we'll cover in the next module. So this is the end of this part of the tutorial. So just to kind of go over what we've covered again. So we talked about how to apply a water mask to the AirSWOT data to exclude the land pixels. We talked about how to filter out outliers and spatially average the data to estimate water surface elevation. And we talked about how to monitor water level changes over time by looking at multiple AirSWOT flight lines that were collected on different times. And we also looked at how to estimate the water surface slope by fitting a plane to the AirSWOT data in 3D coordinates. So this is the end of the second module. Are there any questions before we go further? Oh, yes.
Sorry, I was just asking about the error of, of this. I guess, I was looking at like minus 1.1 centimeters per kilometer. But you were saying at the beginning the error looked pretty large, but then you were saying with multiple overflights it went down. But how small did that error get? Just to
So the error in the water surface elevation, or so yeah. So by averaging, it reduces the error. And I think in the level 3 product that I showed, our estimated uncertainty was like 7.4 centimeters. And for that old, the 2015, the pre-Delta-X data, we did validate it with all of the in situ water level data that we could find. And the RMS error of the water surface elevations was about 10 centimeters. So that's kind of the expected error level of AirSWOT after averaging.
And so can you relate that to what we get as the result here? So I guess I'm having trouble relating that to this minus 1.1 centimeters per kilometer, like some of the results. So does that mean that's within the error or?
Oh, I see. So, so the thing with the slope errors, which is a little different than the elevation errors, is that for the slope errors, the bigger the run of the slope, the more accurate the slope estimate is. So essentially, the more averaging you do, like if you use that 10-kilometer window, you get a more accurate slope than if you use like a 2-kilometer window because you've done more averaging. So since the slope is in centimeters per kilometers, if you have that 10-centimeter RMS error in the vertical heights, and you do a 10-kilometer reach, then you would expect that to be about a 1 centimeter per kilometer RMS error over a 10-kilometer reach. And for the pre-Delta-X data, we did calculate the slope using some of the in situ data. So we used a gauge at the ocean and a gauge at the upstream part of the river near Calumet. And I think the slope errors were generally a little bit less than a centimeter per kilometer, but they were within that kind of ballpark of like a centimeter per kilometer or less. But yeah, it's because we average over those great distances. Yeah, you're welcome. Yes.
So I have a question because we are mainly showing data here for this AirSWOT data over the wetland or over the channel. Do we have such similar data for over the open ocean? Because I think for this surface slope, it's complicated in those channels due to the bathymetry. If we are in a like open ocean area, maybe the surface we can observing a clear patch from the wave movement.
Oh, I see. Yeah. So the AirSWOT data does extend a little bit into the ocean. So I think you could definitely get some slope measurements if I look at one of these, maybe like this one. Yeah, it does kind of extend past the delta into the ocean a bit. So I think you could use this part of the line. And there's some other flight lines that are close to the ocean. So you could estimate some slopes in the ocean. I should give a warning, which is that AirSWOT works best on inland waters. And in the ocean, it's close to the coast, it's okay. But as you get out farther into the ocean, AirSWOT has some issues when you have really large waves, essentially. So there's kind of a sweet spot there where if you're in a place with very large waves, that can cause errors. So it works, there's kind of a sweet spot because if the water surface is too smooth, you don't get a good result because not enough of the radar signal actually reflects back. And if the water surface is too rough, if you have these big ocean waves, it also causes issues. So you kind of want it to be just rough enough, essentially.
Got it. Okay, another question is that I think for a surface in general, if you get the slope of each data point, or at least like several points in an array of the surface, the slope, you can reconstruct the surface. But for the purpose of like this study, we only roughly estimate for this one point, for that as a representing average of the whole area. Do you think is that because of this swap west is too small, or if the swap west is a lot larger, or maybe from satellite, if the satellite can give a much larger swap and in the future is more, maybe the technology improve is more precise, can we reconstruct the surface of the slope from the slope?
Yeah, that's a great question. So I think the short answer is I think yes, we would expect to be able to potentially do better. This was kind of, I guess, a simplified example. When generating the level 3 data products, we sample them a lot more than just like one point in this big lake. So we do have more technically you have more kind of slope estimates along the river channel than just like one point in the middle of the lake. This was, I guess, mostly just for the purposes of an example. The only, I guess, difficult part is if the lake is too small or if the river channel is too thin. And in those cases, it's very hard to estimate the slope.
Thank you.
You're welcome.
Actually, a quick question. Have you ever correlated the mean slope on the lake with wind direction?
Oh no, I haven't. That's a good question. Yeah, I think that would be interesting. No, I haven't done that. We did. I guess that's one of the things that we probably should do. And we did collect some wind speed data in the field during the fall part of the campaign, but I haven't really analyzed that yet. So I agree. I think it'd be interesting to compare the wind speed. Good morning, and hopefully you can hear me. And let's get started today. So picking up from where we left off yesterday, we just finished the second module of the AirSWOT tutorial. And I'm back here on the GitHub page we were on yesterday. And I just opened down here module 3, comparing AirSWOT to in situ data. I just opened that in Google Colab. And once you open that, you should see it right here. So this is what we're going to talk about. Oh, yes, Alex.
Sorry, Michael. Can you just, in case there are some people online who weren't here yesterday, can you give us a recap of what the GitHub is and the notebooks and stuff, just briefly?
Oh, yeah, no, for sure. Thank you. So yeah, the GitHub is right here. I don't know if you can see that online. Maybe I'll try to
I'll put it in the chat.
Okay, thanks. So yeah, the GitHub is here, and so the first module that we did yesterday was an introduction to the AirSWOT data, and the second module that we did yesterday was on estimating water surface elevation and slope using AirSWOT. So as you'll recall, in the module we did yesterday, we estimated the water surface elevation for a lake in the Terrebonne Basin. And today we're going to compare the water surface elevations that we estimated from AirSWOT with some in situ data from one of the CRIMS stations. And we're going to do that to validate our AirSWOT water surface elevation measurements. And another useful thing we can do with AirSWOT, which we're also going to talk about today, is if you have gauge data where you don't know the datum, or maybe it isn't really referenced to a vertical datum with respect to an ellipsoid or a geoid, it's just a raw gauge height that's not referenced to anything. You can also estimate the difference between the gauge data and the datum by just estimating the difference between the gauge data and AirSWOT. So we're going to do both of those things today. We're going to try estimating what we think the gauge datum should be from AirSWOT, and then we're going to do the vertical datum transformation ourselves, and we're going to check that to see if it matches. So I'm going back into this Google Colab now, which on the GitHub, it's the third one down under module 3. So you want to click that button, and it should open this one, which says comparing AirSWOT to in situ data. So again, as we did yesterday, you want to run the first cell, and this should set up Google Colab. You'll probably get some pop-ups like this, asking you to sign in and give permissions. So I'm going to do that now. Oh, it's going to make me do this again. I should have known. And then after you authenticate yourself, you should be able to run that cell in the notebook. And it's going to ask you if you want to allow the notebook to access your drive, and all of this should be the same as before. Oh, I think I may have accidentally stopped that from finishing. And there we go, it finished. So now our Google Drive is mounted in the Google Colab notebook. And same as the modules we did yesterday, if you're following along on Google Colab, this path should work. If you have the data on your local machine, you should change it to wherever you saved the data. And this next cell sets a path to save the data. If you're running on Google Colab, you don't actually need to use this because that part of the notebook didn't work very well on Google Colab. So I changed it slightly. So if you're running on Google Colab, it doesn't need to save any data. It will just load some data that I exported for us for the purposes of the tutorial. So now we're getting into the actual code of the notebook. So we're going to use the Python datetime module again to help handle the dates and times of the in situ data and AirSWOT. And the rest of these libraries were things we used in the previous modules as well. So the OS library just helps handle the paths, and then NumPy does a lot of calculations with arrays. And then we have GDAL for the geospatial part, which is especially important for this module because we can use GDAL to help with the datum transformations. And then we use matplotlib for plotting, and we use pandas to help load the station data in a similar way that in the first module we used pandas to load the AirSWOT level 3 data. The station data are also CSV files, so we can load those with pandas, and that's what we'll do in this module. And this part here is just, these are the water surface elevations, and these are the dates that those AirSWOT flight lines were collected. And this is the same results we got yesterday from module 2. I just copy pasted them to this one, so we didn't need to calculate these again. And then this next set of files, these are another set of AirSWOT height products, and we're going to use those a little later in the module for another example of a vertical datum transformation. But for that one, we're going to do it around the USGS Calumet water level station, which is in the Wax Lake outlet. So once you've run this cell, you can go down, and the next cell is to load the CRIMS data. And if you'll recall, in the previous module we did, I pointed out the location of a CRIMS station next to the lake that we looked at. There's a little green dot on the map, and that's this same CRIMS station that I'm loading the data for now, which I should have mentioned is CRIMS 0434. So I just, so you can find this CRIMS station on the CRIMS website if you're interested. So now we're going to load the CRIMS data using pandas. So pandas has this read CSV function, which is very useful. And we just load the CRIMS data using pandas, and then we're just going to print the CRIMS data as well as the column names. And the CRIMS height is in feet, so we're going to convert it to meters, since the AirSWOT data is in meters. And we're going to get the dates and times of the CRIMS data. And since those dates and times are strings, I'm going to do something similar that I did with the AirSWOT data, where I just parse each part of the date and time, and I just convert them to integers. And then we just convert them to date time using the Python datetime class. So so this is just the year, month, day, hour, and minute. And the second is always 0 for the CRIMS data. Another thing we need to think about is that AirSWOT data is always in UTC time. However, the CRIMS data is in local time. So in this case, we have to shift the data by 5 hours. So that's what I do here. This is the handy thing about using the Python datetime module. If you want to do that, you can just use this time delta from the datetime module. And if you say time delta hours equals 5, that will give you a time shift that you can then just add on to the date time. So here I calculate the crims as a Python date time. And I'm just using the year, month, day, hour, and minute, and then the seconds are 0. And I just add the time shift on the end for the time zone. And this part of the cell just subsets the crims data. So Pandas loaded that entire CSV file, but it has a lot of dates that we don't really care about for this module. So I just said the start date time should be April 15th. And if you recall, the first AirSWOT flight we looked at was on the 16th, and then it ends on the 20th. And I only select crims data where the date time is less than the end date and greater than the start date. And then I just subset the date time and the crims height to that date range. So we're only going to look at the period from April 15th to April 20th when our data was collected. And below the cell here, you can see this is just the printout of the crims data. There's a lot of fields in the crims data, so I'm not really going to go into all of them. But when you're loading data, it's usually good to just print out the columns and see what's there, as was mentioned yesterday in the field data workshop as well. So now that we've loaded the crims data, let's plot the crims data and the AirSWOT water surface elevations. So as you can see here in the plot command, I just plot the date time as the X and the height as the Y variable. And same for the AirSWOT. We just plot water surface elevation versus date time. But as you can see here, the values are of course very different. And this is because we haven't accounted for the different vertical datum of the crims data versus AirSWOT. So since AirSWOT is with respect to the WGS 84 ellipsoid, in this area, it's around -25, -26 meters is where the AirSWOT water surface elevations are. But the crims data, which is generally with respect to NAVD 88, if you look in the crims data, there will be a field that lists which geoid model was used for a given data record. And I think for the most part, they use geoid 12B, I think in most of the recent data, which is just that specific version of the NAVD 88 datum, which we'll talk about a little more later. So how do we get the AirSWOT data and the crims data on the same datum? So we can start by just assuming that maybe we don't actually know what the datum of the crims station is. Maybe someone just sent us water level data and we don't know what it's referenced to. So in that case, one way to do it is just to estimate the mean or median difference between AirSWOT and the crims station and just adjust the station data by that amount. And then that tells you, of course, if AirSWOT is biased, then your result for that datum transformation will also be biased. But if nothing else, it does demonstrate that the relative water level change between times is consistent between AirSWOT and the station, because when you're transforming the vertical datum, it should always just be, of course, one number that you add or subtract from the station data. So I'm going to run this cell next. And this cell, this just has a little function here to help you interpolate the water level data, because of course the crims data is sampled at different times than the AirSWOT data was collected. So what this function does is it just interpolates the station water levels to the same time that the AirSWOT data was acquired. And it just does that with piecewise linear interpolation. So it finds the two closest data points in the crims time series on either side of the AirSWOT time, and it just linearly interpolates between them. And that's what we've done in this cell. And so we calculate for each of the AirSWOT date times, we just calculate the CRIMS water surface elevation interpolated to that time. And then we take the difference between them. And then we take the median of the differences, and that's our estimate of the datum transformation. You could use the mean as well. I usually use the median because in case there is an outlier, it generally works a little better if you want to use the median. That way, at least you know that at one of the times, it should be pretty close. I also print here the standard deviation of the differences. So the standard deviation of the differences should be small if that offset is consistent over time. So as you can see here, these are the differences between AirSWOT and the CRIMS water levels for each of those 4 times we looked at. And this is the median difference, which is 25.98 meters. And the standard deviation of the differences is 3 centimeters. So we're pretty close. We have a pretty consistent difference between the AirSWOT and the station data. So according to our estimate, we need to subtract 25.98 meters from the CRIMS station data to get the CRIMS station data to the same datum as AirSWOT, which is with respect to the WGS 84 ellipsoid. So this is the same plot that I showed above, where they were very different. Just now I've subtracted 25.98 meters from the CRIMS data. And you can see they line up pretty well. So this April 16th flight, as you can see, was collected when the tide was receding, and then the April 18th flight was when the tide was rising, as you can see there. And so it looks pretty good. It looks like our datum transformation is consistent over time, which gives us confidence that it's accurate. But since this is CRIMS data, we do know that it is generally referenced to the NAVD 88 geoid. So we don't necessarily need to just estimate the datum transformation from AirSWOT. We can do that ourselves. And there's a lot of ways to do the datum transformation. Today, I'm just going to talk about a couple different ways. The way that we're going to use first, and I think this is probably the easiest way to do it, because you don't have to install anything, is just to use the NOAA VDatum tool. This tool's provided by NOAA, and there's a downloadable version of the tool if you want to run it on your machine. But there's also an online conversion tool, and we're going to use that today since it's a little easier. And we don't need to install anything. So if you click that link there, NOAA VDatum online conversion, it should take you to the NOAA VDatum site, and you should see something like this. So we're going to fill this out in a sec. I'm just going to scroll down here a little bit, because the first thing we need to know to do the vertical datum transformation in VDatum is where our station was actually positioned. So I just printed the latitude and longitude from the station data, and so they're right here. I'm going to start by copy pasting the latitude, and if you're in the Colab notebook, I have some screenshots here showing you kind of what to set. But since we're here, I'm going to show you how to do it. So we're just going to kind of walk through each step, and by the time we're done, we should have filled in the same things as that screenshot in the notebook. So the first thing at the top here, it asks for region. So that's going to be contiguous United States, where we are. So if you choose that, you're going to see here you have a source datum that you have to pick and a target datum. So let's say we want to start with AirSWOT, which is in WGS 84, and we want to get to NAVD 88, which is the datum of the CRIMS station. So that means our source will be WGS 84, and our target will be NAVD 88, which you can see is already set here. I think that's the default. So under source, you want to change this reference frame. Well, our source data, the AirSWOT data, isn't in NAVD 88. It's in WGS 84. And we're going to scroll down here, and it can be confusing because there's a few different versions of WGS 84. There have been revisions to it over the years. Same with NAVD 88. Since the geoid does change over time, there's revisions over time of the geoid. So there are all these different systems, but we're just going to use WGS 84, this one that says use ITRF 2008. That should be a pretty recent version, and it's the one that is used by AirSWOT. So now we've set WGS 84. You can see when you changed it here, it also changes above. So based on the vertical datum you've chosen, it assumes that your, what it calls the reference frame, which is the spatial reference system, essentially, of not just the vertical information, but also the horizontal positions. And so that's changed as well. So now we're going from WGS 84. And you can see here the coordinate system is set to geographic, longitude, latitude. You can change that. If you wanted to use the UTM coordinates, you could change that. Since our station data is already in longitude, latitude, I'm just going to leave that alone. And here, whoops, this one. So under NAVD 88, we can check this box that says geoid model. And there's a few different geoids you can see here. As I mentioned, NAVD 88 has changed over time because the geoid has changed over time, as well as the estimates of that geoid that go into this model. But we're going to use geoid 12B. That should be the same one that the CRIMS data uses for this station at this time. So now we've set the source and the target. So we're going from WGS 84 to NAVD 88, and we're going to use the geoid 12B model. And now we just need to put in the input position. So I think I copied the latitude from the notebook. I'm just going to paste that in. And I'm going to go back to the notebook, and I'm going to copy paste longitude value as well. And for the height, I'm just going to set this to 0 because I really just want to know the difference in height. I don't really care if, if I put 1 meter there, it would just change the output by 1 meter. But I really want to know the difference between them because I want to know how much to add or subtract to my data. So I hit the transform button, and it doesn't give you the answer right away. It takes you to this page. And this page is related to what I mentioned earlier about the fact that these datum transformations change over time. So it asks you to specify the date of the input and output position. And this can be kind of tricky, especially for the input position, or I should say if you don't know when a particular data set was surveyed, it can be kind of tricky. I will say this, the amount of this shift over time is usually pretty small. So even if you have maybe a slightly wrong date, we're talking on the order of maybe like a few centimeters will usually be the errors you get, unless you have a really big difference, like you're using a position that was collected in like the 1990s, but you say it was in 2021. But this time it's pretty easy because we know the AirSWOT data and the CRIMS data were both collected in 2021. So I'm just going to put that there. I'm not going to worry about the decimal of the year since we're in April. It's a pretty small difference. So I'm just going to put 2021 for both input and output positions. And after doing that, it should take you back to the first page that you started on. But now the output position is filled in. So you see here that a height of 0 with respect to WGS 84 is equivalent to a height of 25.948 meters with respect to NAVD 88. So I'm just going to copy that, 25.948 meters. And then we're going to go back to the notebook. And hopefully this is clear so far. If anyone has any questions, please feel free to stop me at any time. And I'm just going to scroll past these because these are the the things we just filled in. And now I'm going to go down here to the next cell. And this time, rather than trying to bring the CRIMS data to the AirSWOT, we're going to go the other direction. So I took the 25.948 from the VDatum tool, and I just added that to the AirSWOT elevations. And I'm going to run this cell, which should regenerate the plot. And as you can see, they agree pretty well. They're not perfect. I think the difference between the datum conversion that we got from the VDatum tool and the one that we estimated ourselves is about 4 centimeters. So it's within the uncertainty of AirSWOT. So there is a small difference, but we're pretty close to the actual CRIMS data, as you can see here. But there is, I think, a small 4 centimeter bias. And yeah, so that is the section on the Terrebonne data. And I'm going to switch gears a little bit, and we're going to move back to the Atchafalaya Basin for the last part of this module. So the reason we're going to do that is I want to show you not just how to convert the datums for an individual point data, like the station data, but it's also interesting to convert the datum for all of the AirSWOT data for the whole image. And you can actually do that using VDatum as well. I think if you download the VDatum tool, it can convert geotiffs. So that's probably the easiest way to do it. I wanted to show a way to do it in Python as well. This is the part of the notebook that I ran into some issues with, where Google Colab doesn't seem to like doing this. So I had to disable part of this notebook if you're running it on Colab. But I still want to go over this because I think it's useful to know. And so GDAL can convert between vertical datums if you use this GDAL warp command. And this is what this example does. And I have this use GDAL that I've set to false in the notebook, since this doesn't work correctly on Colab. But if you had GDAL installed on your local computer, this should work. So what I've done here is that save data path that I specified at the top of the notebook. If that path doesn't exist, it just makes the directory. And then here we set the warp options. So we go gdal.warp options, and then this lets us specify all of the parameters that we want to use for our transformation. So here I've said format equals gtiff, which is short for geotiff. So that means I want the output data to be in a geotiff. And you don't actually need to specify that as long as the input and output formats are the same. And then here I have source SRS, which is the source spatial reference system. And I have the destination SRS, which is the destination spatial reference system. And so I specify that the projection of the AirSWOT data is in UTM, and we're in zone 15. And then I mentioned that we're in UTM coordinates, but it's with respect to the WGS 84 ellipsoid that we're working in. And the units are in meters. And then that's the source, but the destination, we don't want to be in WGS 84. With respect to the ellipsoid, we want to be with respect to the NAVD88 geoid. So I've added an additional parameter, this plus geoid grids equals G2012 BU0.GTX, which is a little confusing. But this file essentially is just a file that specifies the value of the 2012 version of the NAVD88 geoid. And this is the part that didn't work on Colab. If you've installed Google or installed GDAL on your local machine, you should have this file already in GDAL, and it should know where to find it. But I think on Google Colab, some of that doesn't seem to work quite correctly. Another thing you can do is here I've just specified this G2012 BU0.GTX. You can actually specify the path to another file And if you want, you can download those files yourself. You don't have to rely on the ones that come prepackaged with GDAL. And I have a link here in the Google Colab notebook. I'm not really going to go into that because I don't think we have too much time, but if you're interested in this, there are places you can go and you can download these GTX files for yourself, and you can use your own if you have troubles with GDAL. And then after setting up those warp options, what we do here is we just loop through each file in our list of files that we want to use. And then this just changes the file name to the output file name. So I changed instead of .hgt.tiff, I just changed them to hgt_navd.tiff. And then to actually do the transformation, you run gdal.warp. And you just give it the output file name, and then the input file name, and then the options that we set. And that will take the source data set, it'll run the warp using those options that we specified, and then it will spit the output to this file. But since that didn't quite work on Google Colab, I did something a little different, which is that I used GDAL on my computer, and I just spit out what the value of this geoid should be as a raster file, and I added that to the sample data that's in the notebook. So that I should say the sample data that's on the Google Drive. So we're going to just use that data that I exported on the Google Drive, and we're just going to interpolate it the same way we did with the water mask, and that'll give us the height of the geoid for each pixel in the AirSWOT data. So I'm running this cell now. This cell's a pretty big one. It kind of does a lot of things that we did in the previous module, so I'm not going to go into every one, but essentially these functions to interpolate the data and to interpolate the data at specific map coordinates and to convert between the coordinates of the image and the map coordinates and to filter the outliers of the heights. These are all just copy-pasted from the module that we did yesterday. And same as yesterday as well, I load the water mask. This is the part that's new, where I load the geoid file that I saved. And then same as the water mask, I get the geoid file using GDAL, and then I read the data as an array, and I get the geotransform so that I know where that data is. And now we do the exact same thing we did for the Terrebonne data, where we find the position of our target of interest. In this case, it's the USGS gauge at Calumet. And I find the location of the Calumet station, and we cut out an image chip around the station, and we interpolate the water mask for that chip. We interpolate the geoid for that chip. And you see here, we take the heights from AirSWOT, and we subtract the geoid height, so that now the AirSWOT heights are with respect to the geoid rather than the ellipsoid. And then we mask the data with the water mask and apply the outlier filter. And then this is copy-pasted from the second module as well, but it just parses the AirSWOT file name into a Python datetime object. And then after doing all of that masking and filtering, we calculate the water surface elevation, again, as just the mean water surface elevation in the image chip. And then we print the results, and we plotted a time series of the water surface elevations. So I'm going to scroll down past this plotting code. So kind of similar to the Terrebonne example, the code above, for each date and time that the AirSWOT data was collected at, it spits out our estimate of the water surface elevation around the USGS Calumet station. And this time it's with respect to the NAVD 88 geoid, since we transformed it. And this is what that data looks like. Since we did the vertical datum transformation on AirSWOT, it's already in NAVD 88, so it should be close to the Calumet gauge data, which is also in NAVD 88. But we're going to confirm that in a moment. And here you can see each of these is the image chip that I used to estimate the water surface elevation. So this red marker is the position of the Calumet gauge. So the image chip is centered around that. And then, so you can see this is the wax lake outlet in the middle of these image chips. It's a little clearer in some of these images rather than the first two. The reason for that is that in these first two images, we had issues with what I mentioned yesterday, where if the water is too smooth, we don't get a lot of radar signal reflected from the water. Usually that happens if the wind speed is really low or the water is just unusually calm. So we like a little bit of roughness on the water. And unfortunately, you can see upstream here, all of this is void data. And this wasn't masked out by the water mask. This was already void data in the AirSWOT files because we didn't get good water surface estimates there. But on March 26th, you see the first one was you didn't get anything. The second one we got a little bit, but there's still some void data. But that implies that between these two flight lines, the wind speed picked up a little bit for the second image. But on the other days, it was fine. So it just depends on the wind conditions. Usually if the wind speed is less than around 3 meters per second, that's kind of our rule of thumb for where we expect to see issues like this when the wind speed is below 3 meters per second. Usually as long as the wind speed is above 3 meters per second, it will be good, which was the case for the March 27th and the April 1st flights. So this first row of images is before the water masking and the filtering, and this next row of images is after water masking and filtering. So you can see these yellow parts are the higher elevations on either side of the river. As well, there are some pipes that cross the river here, as well as a bridge. So those are also in the AirSWOT heights. And those are gotten rid of by the outlier filter that we ran because their heights are much higher than the height of the water surface. So the outlier filter got rid of them. And you can see here on these bottom row of images, on March 26th, we didn't have as much data to work with, but still all of the land pixels and the pixels corresponding to the bridge and the metal pipe that crossed the river have been removed. So now that we've calculated this list of water surface elevations at these different times near Calumet, it's time to load the Calumet gauge data and compare that to our results. So I'm going to run this next. So as we did with the CRIMS data, we load the Calumet data using pandas. This time there's a header in the USGS Calumet station data. So if you do download that, just keep that in mind. I had to specify skip rows equals 29 just to make it skip the rows that were at the beginning of the file. And again, after loading the data, I print it. And the Calumet height data is also in feet rather than meters, so we convert it. The station data that's in the file isn't with respect to NAVD88. Instead, they give an offset. If you go to the station information page, they give you an offset with respect to NAVD88, which I apply here. There's another offset because the Calumet station data was surveyed quite a while ago. So even though it's NAVD88, it used a different version of NAVD88, an older version than I used. So the offset between those two geoids is about 20.7 centimeters. And this was calculated using VDatum as well. If you go back to VDatum, I'm not going to really go into this, but you don't just have to convert from WGS84 to NAVD8, of course. You can choose NAVD88 as both of these, but you can specify that one you want to be geoid 96 and one you want to be geoid 12B. So you can convert between the different versions of the NAVD88 geoid. And when I did that, I got 20.7 centimeters to subtract from the Calumet gauge data. And this code just does what we've done before. It just parses the date times from strings into integers. The Calumet data is also local time, while the AirSWOT's in UTC, so we do the same time shift, which we've applied here. And as with the CRIMS data, I'm going to subset the time series from March 26th to April 3rd, which is around the time that the data was collected. And then we just subset the data that we loaded to that date range. So this cell prints out the Calumet data that we loaded. And you can see here this raw water level field. This is the one where we got the water levels from. And then you can just see here, this is the list of the columns. And you can see from the time zone here that it was in Central Daylight Time, which is why we needed to convert it to UTC. So now that we've loaded the Calumet and the AirSWOT, now that we've loaded the Calumet data and converted the AirSWOT heights to NAVD88, they should be on the same datum. So let's take a look at that now. And they're pretty close. So this is the March 26th flight. Very good, actually. Captures an increase in the Calumet water level. March 27th didn't work quite as well. You can see here we're off by about 5 centimeters or so. So that is within the uncertainty that we expect from AirSWOT. We don't expect to always get perfectly accurate elevations, but it's pretty close. It's within about 5 to 7 centimeters. And if you recall from previous studies where we've validated the AirSWOT data more rigorously, which I should mention again, hasn't been done for the Delta-X data sets yet. We're still in the middle of that, so this is very fresh data. But from our previous work, we got an RMS error around 10 centimeters for AirSWOT. So that's kind of the ballpark that we expect. And then the April 1st flight also did pretty well. It was very close to the Calumet gauge data. So, and that's basically it for this module. Hopefully that gives you an idea of how to do these sort of datum conversions using the NOAA VDatum tool and GDAL, and hopefully that helps you understand how you could compare AirSWOT to gauge data if you have some gauge data that you want to either check with AirSWOT because you don't know what datum that gauge is referenced to, or if you just want to validate AirSWOT, which is what we usually use it for. And so let me just wrap up and give a kind of overview of what we covered. So we learned how to load the in situ station data with pandas and compare the in situ water surface elevations to AirSWOT. We also learned how to estimate the datum of the gauges using AirSWOT, how to use NOAA VDatum to calculate the vertical offset between datums. And we didn't, I showed you the code, but it didn't quite work on Google Colab, but hopefully this gave you an idea of how to use GDAL warp to also convert the AirSWOT height data from WGS84 to NAVD88. And that's the end of the third module. So I'll stop here for questions if anyone has any, and my email is also here at the end of this notebook. So if you think of any questions later or anything you'd like to ask me about regarding AirSWOT data, please feel free to contact me. Yes.
I'm sorry, I might have missed this, but did you hypothesize why the GDAL warp tool didn't work for you?
Yeah, I'm not 100% sure, but I think the reason it didn't work, I'll scroll up here. I think the Google Colab install of GDAL doesn't have these this geoid grid. It couldn't find this file, and I think that's the issue. So I think if you install GDAL on your local machine, it would work because it's supposed to install those files within it. Yeah, I think it's just a Colab thing.
Okay, because in the past, I've had a lot of trouble with that specific tool, in the warp tool. And I've only got it to work on Linux machines. And,
Oh, I see.
I have no idea why that is, just besides, just might be a little bit different.
Are you normally using it on Windows?
It doesn't work on Windows, it works on Linux.
Gotcha. Yeah, I've tried to use it on Windows, and I've always had a lot of trouble on Windows. I think the issue with Windows, it's been a while since I looked at this, but I think for it to know where the files are, there's an environment variable called gdal path. And I think on Windows, sometimes that environment variable isn't set correctly, so it doesn't know where to find the files. I think another thing you can do is you could download these geoid grids, and rather than specifying just the geoid grid, you could specify like the full path to the file. And I think that might be a way to get around it. But yeah, I've had a lot of trouble on Windows. Unfortunately, I'm on a Mac, so it's hard for me to debug the Windows version, but I'm glad it works on Linux. It works pretty well on Mac too, but Windows has a lot of issues, yeah.
Okay, thank you.
Oh, yes.
Thanks. Just a question about the sort of the last plot with the plotting the time series against the 2 or 3 points.
Sure.
Do you see, just generally, I guess, the bias is generally either always negative for one flight or always positive, or does it vary randomly?
It is fairly random. I think this time it just happened to be negative, but we'll see both. Yeah, it seems fairly random.
Okay, and then is that sort of indicative of the whole flight path, or is it really just about where you are in the flight path comparing to that gauge, or?
Yeah, great question. It's just really that part of the flight path, since it can vary along the flight line, and it can also vary between flight lines of the same flight. So it does change. That's something that I guess yesterday when we looked at the Terrebonne data, I mentioned that the April 12th flight had a larger error, so I needed to still look at that. And for the April 12th flight, it wasn't the whole flight line, but it seemed like the part that happened to be close to where we were looking at was just off by a bit.